All right. Good morning, good afternoon, good evening, everybody. Hope you guys are doing okay. If you're alive, that counts. Um, so we're going to be going through friction and incline forces and stuff like that. So let's go ahead and get started. So the first thing we're going to do is damn, 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 damn. Okay. Okay, cool. That's okay. It's all right. I'll just remember to edit that out or something. I don't know. Okay, so let's go ahead and get started. Give me a second. Okay, so let's go ahead and get started with this first example. We're just going to be covering some basics over friction, some easy friction. Okay, so let's say this block has a mass of m being, let's give it 10 kilograms. Let's say the coefficient of static friction is going to be equal to 0.2, 0.41, 0.41, and let's say you are applying a force to the left of this, force F. Okay, so now the question is, what is force of static friction when the force you're applying is equal to 0 newtons? Go ahead and pause the video. I encourage you to take an attempt at this and play the video when you have gotten an answer. Okay, so considering you've gotten this far, I will assume that you have taken an attempt. So which way is, if we're applying force this way, which way does static friction, which way is the force of static friction applied? So the force of static friction is applied in this direction. It's opposing the force of movement, force of static friction. If we had a bunch of forces going this way, this way, this way, it will depend on the net direction of the forces. So if you add all of them up and the net is this way, then the force of static friction will go this way, given that the block is not moving. Static friction is only present when the object is not moving. Okay, so let's see. If we apply a force of 0 newtons, let's see. Coefficient of static friction is 0.2041, which is equal to the force of static friction, which is proportional to the force with the force normal. So by this right here, force normal, we have force of gravity, which is going to be going down this way. Force normal in this case is going to be equal to force of gravity because the sum of them has to be 0 because it's not moving vertically. So force normal in this case is going to be equal to force of gravity, which is going to be equal to 10 kilograms times 9.8 meters per second squared, which in total is going to be equal to 98 newtons. So if we manipulate this, 0.2041 times force normal is equal to force of static friction. So if we do that, what we're going to get is 0.2041 times 98 is equal to the force of static friction, which in this case is going to be equal to is going to be equal to approximately 20 newtons. So the answer is 20 newtons. Is that right? Well, let's imagine it. The force of static friction is going to be opposing the force. So it's going to be 20 newtons in this way. But we're applying 0 newtons of force this way. And if this block is not moving, because the force of static friction is only present when the block is not moving, this doesn't make any sense. And the truth is, I led you astray to see if you would catch my mistake. This coefficient of friction is going to be, static friction is going to be force of static friction maximum over the force normal. So in other words, the maximum amount of force this static friction can apply is going to be 20 newtons at maximum. But force of static friction is just going to be equal to, for any force that's less than that, is going to be equal to the force that is going to be equal to a force that opposes motion. So in this case, if our force is going to try to move this block, and we apply 0 newtons of force of static friction is just going to be 0 because it doesn't need to apply a force to oppose motion. Force of static friction in this case is going to be equal to 0 newtons. Now what about 10 newtons? Now we've already established that the maximum that force of static friction can be is 20 newtons. So the range that static friction will the range of forces that static friction will apply will be anywhere between 0 and 20 newtons. So if we apply if we apply 10 newtons of force this way, it makes sense for the force of static friction to apply 10 newtons of force this way to oppose the force that's trying to set this block into motion. So force of static friction in this case is going to be equal to 10 newtons. So what about 20 newtons? In this case, force of static friction, this is going to be the upper limit. And if you follow the same logic, 20 newtons of force this way, 20 newtons of force this way. Force of static friction is going to be equal to 20 newtons. Now I ask you, what about 30 newtons? What is the force of static friction equal to then? Well, could it be equal to 30 newtons? Well, no. The maximum force of static friction, the maximum amount of force that static friction can apply is going to be 20 newtons. So since that is the maximum is going to be 20 newtons. So is the force of static friction equal to 20 newtons? Well, if we apply 30 newtons this way, if we apply 30 newtons of force this way, and the force of static friction is going to try to oppose that, 20 newtons, right? We can see that 30 newtons is greater than 10 newtons. So you're going to have a net force. You're going to have a net force of 10 newtons. And since there's a net force, there's going to be an acceleration of this mass. And if there's an acceleration, this block is moving. Static friction only exists when an object is not moving. So in this case, the force of static friction is going to be equal to 0 newtons. Now, if there was if we had a coefficient of kinetic friction in this case, then the force of kinetic friction will then take place. Kinetic friction will then ensue instead of static friction. Static friction is only present when the object is not moving. Okay, so on to the next point. Okay, so this is about okay, so on to the next point, kinetic friction. Okay, so same stuff. Mass of this block, let's say, is equal to, it's going to be equal to something. And this block is already in motion. It's already in motion. So I'm gonna say that V, this is V, and V is going to be greater than 0, so that it shows that this block is in motion. And there is friction here, force of kinetic friction, mu kf. Kinetic friction is going to be, I'm gonna set it to 0.10. Okay. Okay, cool. So I want you to try to find the force of kinetic friction if m is equal to, and let's start that m is going to be equal to 10 kilograms. What is the force of kinetic friction in this case? Go ahead and pause the video and take an attempt. Alright, so how you would approach this is, you know that the kinetic friction, the coefficient of kinetic friction is going to be the force of kinetic friction over the force normal. And in this case, force normal is applied in this way, and force of gravity is going to be applied this way. So force normal is going to be equal to a force of gravity in this case, but in the opposite direction, of course. So we just manipulate that, and we see that 0.10 times force normal, which is equal to force of gravity in this case, is going to be 10 kilograms times 9.8 meters per second squared. This is going to be equal to the force of kinetic friction. And in this case, it is going to be 10 times 9.8 times 0.1. It's going to be equal to 9.8 newtons. So force K of kinetic friction is going to be equal to 9.8 newtons. So what about, well, let's say the mass of the block is going to be equal to 20 kilograms. What then? What then is going to be the force of kinetic friction? Go ahead and pause the video and take an attempt as well. Okay, so the force of kinetic friction in this case is going to be equal to 19.6 newtons. How did I do that? Same logic as before. The force of gravity is going to be the only thing that determines the force normal. So force of gravity, force normal. Force of gravity in this case is going to be 20 kilograms times 9.8. Then multiply that by the coefficient of kinetic friction, and you get the force of kinetic friction, which in this case is going to be equal to 19.6 newtons. So as you can see, the greater the mass in this case, the greater the normal force, the greater the force of kinetic friction. And this makes quite a bit of sense. Let's say you have some kind of sled. And you pull on this, right? You pull on this with some kind of force. This has and the ground has, the ground is like real life floor. It has some coefficient of kinetic friction, which means there's going to be friction between this sled and the ground. So when you pull on this with force F, it feels like this. So let's imagine you put some luggage on here. This luggage is quite heavy, and you pull. It's going to be a lot harder to pull in this case. That's because the force of kinetic friction is going to be greater. And so in this case, as you can see, the force of gravity increases. As it increases, so does the force normal. It increases as well. In this case, it increases. So let's say that. And let's make another example. Let's say this is a house, and this is you trying to pull this house because you have to move. This is how normal people move. You have to move to somewhere else with your new house. You apply some force on here, and the house is quite difficult to move. Let's tie some balloons on here, which will apply some upward force. We're gonna call it force balloons. This house has some force, the force of gravity, and the force normal, which keeps it above ground. So the force normal minus force of the balloons is going to be equal to force of gravity. So as you can see, if you manipulate this, the force normal is going to be equal to the force of gravity minus plus the force of balloons. Plus the force of the balloons. That doesn't make any sense. Hold on, something's wrong here. Okay, so this is plus. My bad. The force normal plus the force of the balloons equals to the force of gravity. And if you manipulate that, you'll get that the force of gravity, the force normal is equal to the force of gravity minus the force of the balloons. So what does this mean? Because of the balloons, it makes the house lighter. And because of that, the ground does not have to push up on the house as hard as it would have to if there were no balloons. The house sitting on the ground will push up on the house, the same force that the house is pushing down on the ground to keep it still. And when you make the house lighter, the ground has to apply less force. And in that way, because this is lighter, this then becomes easier to move. I said all that just to make the point that as force normal increases, as this increases, the force of kinetic friction will also increase. If this decreases, then the force of kinetic friction will also decrease. It scales with force normal. Okay, so let's see. What is FKF? If M is equal to 20 kilograms, I'll write that a little clearer, 20 kilograms, and we have an applied force. Force applied, which I'm just going to call it force A for simplicity. We apply it in this direction, force A. Let's say that the force A is equal to 10 newtons. Actually, no, 20 newtons. Let's make it 20 newtons. What then is the force of kinetic friction? Okay, so how would we approach this? So let's see. We know that the coefficient of kinetic friction is going to be equal to the force of static friction. No, not force of static friction. Force of kinetic friction over the force normal. Manipulate this and we get mu kF times force normal is going to be equal to force of kinetic friction. Well, what is force normal equal to? Well, in this case, force normal, let's write down this equation. This force normal plus force applied is equal to the force of gravity. Force normal plus the force that we apply is equal to the force of gravity. And if we manipulate this and we try to solve for force normal is going to be equal to force of gravity minus force that we applied. And do we know these? Well, force of gravity is just mass times mass times gravity. And the force that we applied is given 20 newtons. So this is going to be equal to 20 kg times 9.8 meters per second squared minus 20 newtons. And this right here is going to be equal to 196 newtons. I believe. Hold on. Yeah, 196 newtons minus 20, which is just going to be 176 newtons. So in this case, force normal is equal to 176 newtons. Force normal, 176 newtons times the coefficient of kinetic friction, which is 0.10, is equal to the force of kinetic friction, which is just going to be 17.6 newtons. So force of kinetic friction, in this case, is equal to 17.6 newtons. So what about if we apply 100 newtons of force? What is force of kinetic friction then? Well, let's see. Do we know force normal? Well, force normal is down here. Force of gravity minus force applied. Again, if you're writing down these formulas hoping you can use them in the future, please do not do that. I suggest that you learn how to draw free body diagrams and then derive the formulas from that. If you're able to do that, then you won't ever need to write down these formulas. So, gravity, 10 kilograms times 9.8 minus the force applied, in this case is 100 newtons. So that's going to be 196, oh, not 10 kilograms, that's 20 kilograms. It's 20 times 9.8 is 196 newtons minus 100, which is just going to be equal to 96 newtons. So what's going on here? We apply a greater force upwards, making the block lighter, or at least the amount of weight that the ground feels lighter. The amount of weight that the ground will feel will just be equal to 96 newtons. So the block is pressing less on the ground. And if you can imagine that, that will lower the amount of friction between the ground and the block. Therefore, decreasing the amount of kinetic friction from 176 newtons to 96 newtons. All right, one last one. What if we apply 1,000 newtons of force? What is the force of kinetic friction then? Okay, let me clear out a lot of these. Okay, so UKF times force normal is equal to force of kinetic friction. So force normal is going to be equal to force of gravity minus force applied, which is going to be equal to, in this case, 20 kilograms times 9.8 minus force applied, which is 1,000 newtons, so 196 minus 1,000, that is going to be equal to 800 and I believe 4. Yes, 804. 804 newtons. Negative 804 newtons in this case. So let's go ahead and plug this into our equation. 0.1 times negative 804 newtons is equal to our force of kinetic friction, which is just going to be negative 80.4 newtons. So in this case, our force of kinetic friction is negative 80.4 newtons. If you believe me, you have been fooled. I apologize, but this is for the learning experience. The reason that this is not true is because, well, let's go ahead and see if it makes sense. This is moving this way, and we apply 1,000 newtons of force on the block, and therefore, if it's moving this way, the force of kinetic friction applies this way, opposite of the motion. And because it's negative, the 804 newtons will be going this way. So in other words, because we lifted it up with 1,000 newtons of force, we have 804 newtons going in the same direction as the block is going. Well, let's see if that makes sense. If you're pulling on your luggage, or you're pulling, say if you have any siblings or a dog or anything like that, and you're pulling on them, right? You're pulling on them, you're moving them, and then somebody applies 1,000 newtons of force on top of them, above them. Will you shoot forwards With 804 newtons of force, will you accelerate with that amount of force? No, you wouldn't. That wouldn't make any sense. And the reason that doesn't make any sense is because we made a mistake here. Force normal is not going to be equal to negative 804 newtons. Force normal, remember, is going to be the force that the ground exerts on the block. It's going to be equal to the amount of force that the block applies on the ground. Well, how much force does the block apply on the ground? It's negative 804 newtons. It's not applying force on the ground. Therefore, there is no force normal. So in this case, because there is no force normal is going to be equal to 0. And because force normal is equal to 0, 0 times 0.10, that equals 0 newtons of kinetic friction. That will be the answer of that. If you don't understand that, I click on the arrow key, the left arrow key, about 4 or 5 times and listen to what I said again until it makes sense. And hopefully it'll make sense by then, because this is just understanding what force normal is and how that affects the force of kinetic friction. All right, so last bit of practice with kinetic friction. Let's say this block has a mass, same mass as last time, 20 kilograms. And it's moving. It's moving in this direction, V. Let's say we apply a force in this direction. I want you to describe, is block accelerating or decelerating? When the force, when the force we apply is going to be equal to newtons of force, and we'll say that the coefficient of kinetic friction in this case is 0.1. We'll say that it's 0.1 in this case. So go ahead and pause the video, see if you can solve for this. Alrighty, so how we'll do that, we'll go ahead and define this coefficient of kinetic friction is equal to force of kinetic friction over force normal. Let's go ahead and draw vectors. Force normal is applied in this way. Force of gravity is applied in this way. And force of kinetic friction, in this case, is going to be opposite of the motion. So FKF is going to be in this direction. So force normal in this case is going to be equal to force of gravity, and force of gravity, which is equal to 20 kilograms times 9.8 meters per second squared, which is equal to 196 newtons. So what is the force of kinetic friction in this case? Force of kinetic friction is going to be equal to force normal times the coefficient of kinetic friction, which we've established that the force normal is going to be equal to the force of gravity, which is 0.1 times 196 newtons. So in this case, the force of kinetic friction is going to be equal to 19.6 newtons. So what is the net force? The net force will give us an idea of the acceleration. So the net force, if the net force is going to be equal to 0, there is no acceleration. There is no pull in either direction, so it's going to stay, it's not going to accelerate nor decelerate in this case. If the net force is going to be greater than 0, hold on. If the net force is greater than 0, then there's acceleration. And in other cases, if it's less than the force of kinetic friction, then there is deceleration. And this makes sense because if the force of kinetic friction is greater than the amount of force you're applying, the force of kinetic friction will win over time. And if the force you're applying is greater than the force of kinetic friction, the block will accelerate over time. If the force of kinetic friction and your force that you're applying are the same, the block will not accelerate. Yeah, so in this case, we apply 10 newtons of force, and the force of kinetic friction is 19.6 newtons. Net force is then going to be equal to 10 newtons minus 19.6. F net is going to be equal to this, which is going to be negative 9.6 newtons. So it's going to be in the negative direction. So the acceleration is going to decelerate in this case. Okay, my spelling is inconsistent, but you get the idea. Okay, so what about 20 newtons of force? Well, if we apply force this way, does it affect the kinetic friction? The answer is no. It does not affect kinetic friction in this case. That's because kinetic friction is proportional to the force normal, and the force that we're applying is not vertical. It is not in the same direction as force normal, so it will not affect force normal. Nor does it have any components that will affect force normal. So if we're applying 20 newtons of force, the kinetic friction will stay the same. And since it's 19.6, the net force in this case is going to be equal to 20 newtons minus 19.6, which is going to be 0.4 newtons. So it's going to accelerate in this case. Now what if we pull with exactly 19.6 newtons? Well, if you could probably, in this case, go ahead and calculate the force net. As always, it's going to be 19.6 newtons minus 19.6 newtons. The net force is then going to be equal to 0 newtons. And since there's 0 newtons of force in any direction horizontally, there is going to be no acceleration. Okay, cool. And last one. What if we apply 5 newtons of force? Well, is it going to be the same? It's going to be the same case as this first one. If you do the math, it'll be 19.6 minus 5 newtons, which is going to be negative 14.6 newtons. And that's going to cause the block to decelerate. But how would you compare the deceleration of this one to this one? Of this 5 Newton force versus this 10 Newton force. The 5 Newton force will result in a greater deceleration. The block is going to decelerate faster than if you were applying 10 newtons of force. Okay, now we're getting into static friction and inclined planes. That's what they're called. They're called inclined planes. So let's go ahead and start with some stuff. Let's say that the mass of this block is equal to 10 kilograms. The coefficient of static friction here is going to be equal to 0.2. And we apply a force in this direction. And the angle of this ramp is going to be equal to 30 degrees. Let's say 30 degrees. Okay, so in this case, I want you to derive what value of F is needed to overcome the force of static friction. Pause the video and see if you can find an answer. Okay, so let's go ahead and draw our forces. So first off, we have force of gravity going in this way. Nope, my apologies, not this way. Force of gravity pulling straight down. And the force normal is the force that the ramp applies on the block. So it won't be drawn this way. It'll be drawn this way.
because it's perpendicular to the ramp.
Okay, so from here, the force of static friction will be applied this way, opposing the force, the force that we apply. I will go ahead and solve this the wrong way so you understand, so you don't make this mistake in the future.
Okay, so let's see.
Let's see if we can find, we need to find a force that overcomes the force of static friction. So let's find force of static friction so we know what it needs to be greater than. Force of static friction max, oh no, my apologies. Let's define coefficient of static friction. It's going to be equal to 0.2, which is going to be equal to the force of static friction maximum over the force normal. Let's define force normal. Actually, let's manipulate this first. 0.2 times force normal is then going to be equal to Fs max. So let's go ahead and find force normal. Force normal in this case is going to be equal to force of gravity, which is going to be equal to 10 kilograms. Oh dear. 10 kilograms times 9.8 meters per second squared. Okay, so from there we can calculate force of static friction quite easily. It's going to be 0.2 times the force of gravity, which is going to be 10 kilograms times 9.8 meters per second squared. So that is going to be equal to 19.6 newtons. Yeah, it's going to be equal to 19.6 newtons. So the force that we need to apply needs to be greater than 19.6 newtons. Now the reason this approach is wrong is because we didn't break up this force of gravity component into two components, into horizontal and vertical components. Because force of gravity doesn't directly oppose force normal. Force normal is going to be equal to the force that we apply in this direction. Force normal is going to be equal to that, but in the opposite direction. So the forces that we apply in this direction are going to be force of gravity in the y direction. And then in this direction, we also have force of gravity x. This angle right here is going to be the same angle as this one down here. And this is how we will be able to derive this. So let's see. Okay, so let's go ahead and calculate force normal. Again, force normal in this case is going to be equal to the force of gravity in the y component, which is going to be equal to mass times gravity times the cosine of theta. And if you're wondering how I derived the cosine of theta, quite simple. Draw a triangle here. I'm going to rotate this triangle, which is this one, into this one right here. So I'm just rotating it, if you can imagine that. So this part is going to be FGY, and this is going to be FGX. This long component is going to be force of gravity, and this is going to be an angle right here. So from this right here, we can derive that this is the opposite side, this is the adjacent side, and FG times sine of theta is going to give you the length of the opposite side, which is going to be FGX. And FG times cosine of theta is going to give you the length of the adjacent side, which is FGY. And that is how I was able to derive this. This is FG, this is cosine of theta. FG, cosine of theta, FGY. Okay, so next, let's go ahead and calculate this value. It's going to be 10 kilograms times 9.8 times cosine of 30. So 10 kg times 9.8 meters per second squared times cosine of 30. So the force normal is going to be equal to this, which is equal to 84.87 87 newtons. What did I delete that for? Okay, so that's going to be equal to the force normal. So if we multiply that by the coefficient of static friction, 84.87 newtons times 0.2, that is going to give you our maximum static friction, which is 16.97 newtons. 974 newtons. Okay. So now we know the force of static friction max. Now, what force do we need to apply to overcome this? It would just be this, right? It would just need to be greater than this, right? Well, that is incorrect. Let's go ahead and define this. F needs to be greater than FSF. And one more thing, and that's going to be down here. This is going to be in this direction as well. It's going to be a force going in this direction as well, plus FGX. And this makes a lot of sense if we put it like this. We have this block, same amount of mass. It's going to be 10 kilograms, and we pull it this way, and it has the same coefficient of static friction. What the hell? Coefficient of static friction. Same coefficient of static friction. We pull it with F. Imagine you are pulling some kind of, perhaps, let's say, well, I don't think you've ever pulled. Well, let's imagine it that you're pulling something on a flat floor. That thing you're gonna pull it with some kind of force to overcome the force of static friction. Now imagine this again. You pull this same object on a ramp that is inclined, and you pull it. It's going to be slightly harder because you're going to have this part of the force of gravity going in this direction. So it's going to be FSF plus the force of gravity in the x direction. So force of gravity in the x direction, well, this is going to be equal to, if you can recall, it's going to be equal to mg. So it's going to be the force of gravity, 10 kilograms times 9.8 meters per second squared times the sine of theta, sine of 30 degrees in this case, which in this case is going to be equal to 49 newtons. Okay, 49 newtons, correct. Okay, so the force of static friction max, 84.87 newtons plus 49 newtons. This force that we apply needs to be greater than both of these for this block to overcome being still. Which in total is going to be equal to 84.87 newtons. Hopefully you understood. And that concludes this video. Hopefully you understood the topics that I have gone over. If not, do rewatch it. It'll make a lot of sense with practice. This stuff makes sense with practice and application. If you can imagine what's going on, and if you could draw an accurate free body diagram, if that's even what this is called, then you will be fine. You'll be just fine. But do practice. Do practice. Okay. Thank you for watching. Have a spectacular day.